Yeah, so today what we will do is I would like to introduce you to forces and interactions in colloidal systems. Okay, that is going to be the objective of today's class. So, I am going to do that through a little bit of history. Okay. So, this is some really good books. If you are interested, you should read. First one is of course, something on microscopical observations. This is actually written by Robert Brown, okay. And the second one is actually titled Atoms, which is actually written by John Perrin, okay, who was, I am going to tell you a little bit about him and what he has done. It's a translate. I mean, the original book is in French. It was translated to English, okay. And this is a more recent book. It's written by a physicist called Mark Ha, okay, and that's titled Middle World. And if you look at the right, it says the restless heart of matter and life. Okay, so that's these are all very good books. I think you should read up because you'll get a account of some of the developments in colloidal science. Okay. I have taken a lot of contents from this book and this book. Okay, so for today's lecture. Okay, so I am going to show you a movie to begin with. So if you look up, because I copied just the file. Okay, anyway, so there's a movie that's in the YouTube. Okay, what you do is you should go back and just type Brownian motion. You will have several movies that may come up. So what I wanted to show you was that these you have this image, okay, and there are these dark regions and the bright regions, and the bright regions are the particles. Okay, they are very tiny. There is no scale bar here, but the size of these particles I guess is about less than a half a micron. Okay. And then if you see this movie, you will see that they are moving around, okay, they are jiggling around, not in any particular direction. It's a chaotic motion, okay, and that motion comes about because you have these particles embedded in a fluid, and these fluid molecules are constantly hitting or bombarding the particles. Okay, that's what. Okay, so that's what is called the Brownian motion. Okay, Brownian motion is a random movement of particles, okay, suspended in a fluid. Okay, it could be liquid or a gas, okay, and that results from a bombardment or constant hitting, okay, of a atom or a molecule that is in the in the continuous medium. Okay, that's now. So these are some typical trajectories of the particles that were recorded way back in the 1920s. Okay, and this is from the work of Perrin. Okay, and what he did is he used colloidal particles of 0.53 micrometer in radius, and he prepared a sample. He observed them under microscope, and he was able to. So, every point that you see, that is every dot or every point that you see, that is the position of a particle at some time instant, okay, and a later time instant where it has moved. So, he was able to track these particles, and then he has trajectories of 1, 2, 3 particles. Okay, that is what you see here. Now, of course, this is in 1920s, I said, right. Now, way back in 1827, okay. So, Robert Brown, what he was trying to do was he took a droplet of water, okay, and these droplet contained pollen particles, okay, pollen, and he observed them under microscope. So, his intention was to answer questions like this, okay, how does pollination occur, okay, or how do these tiny pollen particles they spread the message of life from plant to plant. Okay, that was the kind of question that he was trying to ask. and he did a lot of experiments, and ultimately he couldn't make a conclusion of what he was trying to do. Okay, okay, and these are actually the particles that were used in Brown's experiment. This is a more recent stuff from 2010. Okay, so these are actually pollen grains from a flower called Clarica pulchella. Okay, so and you look at this scale bar, 50 micron, large enough, but they still he was seeing that they were constantly moving around. Okay, and later on it turns out that these experiments of Robert Brown were essential to kind of answer this question, what the matter is made of. Okay, that means we know that atoms are the building blocks of everything, right? So his experiments were instrumental in telling you that look, atoms are the basic building blocks of everything that is around us, right? Okay, so what Perrin did was he did very controlled experiments. Okay, so unlike pollens, okay, which as you saw, right, they were they come in different sizes, different shapes. Okay, so what Perrin was able to do is he did very careful experiments, and he was able to prove the very existence of atoms. I'll tell you a little bit about how he did that, and this he achieved by a careful choice of particles. Okay, I think that's very important whenever you are trying to do any experiment. So I have some again some pictures from his book. Okay, these are the particles that he used. Okay, they look spherical, they look more or less of same size. Okay, and this is an experimental setup that he used. Okay, that's a microscopy objective. Okay, typically whenever people want to do these Brownian motion experiments, what they do is they take two glass slides. Okay, and your dispersion of particles is embedded between these two slides. Okay, and then you basically seal the entire container, because you don't want any influence of external conditions. There could be some air, all that, right? So you want to minimize all those disturbances as much as possible, and you put this onto a microscopy stage, and then you look around, right? And then you basically record either the frames, images, or the videos, right? That's how you typically do it. So he did those experiments, and because he knew the position of the particles at any given instant in time, he was able to calculate a quantity called mean square displacement. Okay, that is, what is the distance that the particles travel, okay, in a given time. All right, and he knew this observation time. Okay, he had done experiments over a time window, he knew that. Okay, and he was actually able to calculate this d, that is the diffusivity of the particles. This small d here corresponds to the dimension. So d is going to be 1 if you are looking at one dimensional Brownian motion, d is equal to 2 if you are looking at two dimensional system, or d is equal to 3. Okay, so from his experiments he was able to calculate the mean square displacement. Okay, and from that he could back calculate what is the diffusivity of the particles. Okay. Now once you do that, so he used something called as Stokes-Einstein equation, okay, which relates the diffusivity of the particles to this thermal energy, okay, the radius of the particle, and mu, which is the viscosity of the fluid in which the particles are embedded. Because he knew what is R, right? I said that he had done he had microscopy observations of his particles themselves. Okay, therefore, okay, the value of R is known, and from these Brownian motion experiments he was able to calculate d, okay, and viscosity of the fluid he knew, okay, and the temperature at which the experiments were done also he knew. From that, what he did is he calculated Kb, that is a Boltzmann constant, okay, and that is equal to R, which is the universal gas constant, divided by Avogadro number. Okay, because he calculated from his experiments, this is known, he was able to calculate what is NAV. Okay, that is what he did. This is some data from his this is a tabulation of this n, the Avogadro number that is obtained from such experiments. Okay, not bad, right? This is 18 to 10 power 22, right? It's 18 to 10 power 23, right? Fairly close to the Avogadro number. Okay, right? There are a series of numbers. Okay, from this I have taken this again from his book. So he made this statement. Okay, from these experiments, I shall therefore get this Avogadro number to be 68 or 6.85 into 10 power 23. Okay, that's the value he assigns. And then he is also able to calculate what is the charge of the electron, and the mass of the hydrogen atom, stuff like that. Okay, so therefore, Perrin's experiments were very much instrumental. Okay, in kind of coming up in an alternative way of measuring the Avogadro number. Okay, which in turn he was able to kind of conclude that atoms do exist, and the fact that this particles are undergoing Brownian motion is indeed because of the atoms of the molecules of the fluid in which the particles are dispersed. Okay, that's okay. So we'll do an exercise where we'll be able to calculate some numbers like this. Okay, in the next lecture or so. Okay. Now, Brown's experiments 1827, right, and then it took a very long time for Perrin to do these nice experiments and prove the existence of atoms, right. And the reason why he was able to do it and then the other people could not is because he was able to choose perfect particle for his experiments. Okay. Anytime you design an experiment, what is really important is you should ask a question as to what is the aim of my experiment, okay, and what is my objective, okay, and then depending upon what you want to study, you should be able to choose a colloidal system of interest. So that for example, if I was interested to look at sedimentation, for example, okay, then if you do experiments with like say 10 nanometer particles, they would never settle, right, or it will take a really long time to settle, right. So therefore, it's good to ask a question as to, look, this is my objective of my experiments, okay, and then based on that you have to really design a nice model colloidal system, okay, to achieve that objective, right. So now, the how to choose perfect particles. First, I mean, this is okay, the particles must have to behave themselves. That means they should neither attract nor repel with other particles in the system, right, because you are trying to measure Brownian motion of particles, right. This is typically done with a very dilute fluid. That means the concentration of your particles in the fluid is very, very low. Typically, your phi could be as low as 0.0001 or something like that. Okay. The reason for that is the particles have to be sufficiently far. That means there is no interaction between the particles. Okay. That means the motion of the particle is not influenced by the other particle that you have in the system, right. So therefore, the particles in the system should neither attract nor repel with other particles, okay, nor stick to the walls of the microscope slides, because you are doing these experiments under confined walls, okay, and if the particles get stuck to the walls, then what will happen is again it is going to hinder the motion of the particles, right. Okay, so yeah, so he basically says because the particles are immersed in water, okay, which may contain some charges, right, you could have some dissolved ions in the fluid, okay, so all that could influence the the way the particles feel each other. So therefore, it is necessary to avoid what is called the long distance forces, okay, such as electrostatic repulsion. So if you have charges in the system, electrostatics could kick in. So therefore, it's good to avoid all of that when you're trying to do an experiment of this sort. Okay, this is very specific to the experiment that he had done. Okay, now the next thing is that the particles, okay, would have to be as spherical as possible. Okay, what it means is that if you have a particle like this, okay, which is like say a rod like particle, then people talk about what is called a translation orientation dependent diffusion. Okay. You could have translation, okay. You could also have rotation, okay. Therefore, but that's because the Einstein theory, right, that was actually developed for a perfect spherical particles, okay. But as you saw from the microscope image of the pollen grains that were used by Brown, they were aspherical, right, okay. Therefore, the next requirement for his experiments was that the particles will have to be as spherical as possible, but the pollen particles are more often they are either tiny tubes or cylinders, okay. Therefore, the calculation of diffusion coefficient for such things would not be straightforward, okay. This is a second kind of requirement, you can say. Now, thirdly, there is a density problem. What I mean by that is that, of course, you have these particles in a to geometry like this, right. Now, the particles that you are going to use for such experiments should be such that the density should be close enough to that of water, okay. That means they should neither sink to the bottom, okay, or they should not float to the surface, right, because you do experiments for a particular time window. At least in that time window you should never have any influence of density of the particle or the gravitational forces on the particle. Therefore, the particle that you have should always be suspended in the fluid. They should neither sink nor float. And the next requirement is that so the particles have to be of appropriate size. Okay, what I mean by that is that the bigger the particles, the more it resisted being pushed by the surrounding fluid, okay, the slower it moved, right. That means if I am doing experiments with a larger and larger particle, as the particles becomes larger and larger, the inertia becomes important, okay. If it is too heavy or too big, then the solvent molecules only have this thermal energy kBT, okay. They can't move a larger stuff around, okay. Therefore, so the particles would have to be small enough that that means if the particles are bigger, they resist the motion, okay. They do not move because the energy that the molecules have is not big enough to move the particles around, okay. So therefore, the particles too big would have very slow Brownian motion, or they may not even exhibit Brownian motion, right. So if it is very slow, then you may have to do experiments for a very long time, or if they don't move, you don't even have a chance of measuring Brownian motion, right. So therefore, the particles have to be of right size, okay. Now, if the particles were too small, okay, on the other hand, if the particles are too small, they would move very fast, okay. And if it moves too fast, okay, if you have a really good camera, right, with which you can actually capture fast moving things, you can still do experiments. However, maybe at that point in time, okay, so he couldn't do, you couldn't get away by using too small a size because they were moving too fast, and and he really could not reliably track the particles, okay. So therefore, if he was going to succeed in his experiments, Perrin needed particles that had a precise size, and of course they also have to be of they have to be in a narrow size window, okay. And this again comes back to something that we have discussed, monodispersity, right. Okay. That means if imagine that I have tracked these particles, okay, and I have measured diffusion coefficient, okay. Now if they are of different sizes, okay, then I am going to get different values, right. So therefore, or if they are if the size distribution is too big, depending upon whether it is small or the average, or right. So therefore he really needed to choose particles which are of a particular size, and they also have to be as narrowly dispersed as possible. Okay. Now, like whatever the requirement that I have said, right, this is for choosing appropriate size of particles for Brownian motion experiments, for example. Okay. Now, if I were to generalize, this for any experiment, right, can I classify whatever few points that I have mentioned into different classes? So, what I mean by that is that, so if you look at the first part, right, so there is it says that the particles should neither attract nor repel, okay, and they should neither stick to the walls of the container, right. Okay, that is one requirement. The second one is they should be more they should be as spherical as possible. That is a requirement for this particular experiment. And if you look at the density problem, okay, that means they have to be not too big, not too small, okay, and they have to be of precise size and monodispersity. Okay. So, therefore, I can classify these requirements into some categories. Okay. I am going to add another one here. You have to work with model colloids, right, the particles of maybe monodisperse, known size, okay, known surface properties, all of that. Okay. Again, when I say model colloids, it need not be monodisperse always. Okay. There are a lot of people who are trying to look at what is called as the effect of polydispersity. On some colloidal phenomena, okay, or one may be interested to look at, I want to measure what is the viscosity as a function of volume fraction, okay, and I want to compare what if it is monodisperse, okay, versus polydisperse, right. In such cases, you may be interested to look at you may be your model colloids would be both monodisperse as well as polydisperse of controlled polydispersity. Okay. So, therefore, this model colloid requirement need not be always monodisperse. Okay. It depends on again what problem you are trying to look at. So, the other point that we have discussed so far can be kind of clubbed into two main categories. You should have a knowledge of the forces acting on the particles in the dispersion. Okay. That was this gravitational settling, right. So, that I know I can get an idea about whether the particles will sink or float if I know about what is the gravitational force acting on the particle, right. The gravitational force need not be the only force that is relevant in this scheme. We will look at a few different forces that are important. And the second thing is you should have an idea about the interaction forces between the particles in the suspending medium, okay, plus of course the interaction also between maybe the particles and the container itself, right. For example, it could be wall, or it could be if you are storing these particles in the case of Brownian motion experiments is the interaction between the particle and the wall. If you have particles in a like say a beaker, it's the interaction between the particles and the walls of the beaker itself, right. These are also important. Yeah. Any questions so far? Yeah. Okay, we will move on. Okay. Now, okay, let us talk about the forces acting on the particles. Okay. What do you think are the forces that are acting on the system. So, we are talking about, so let us think about like this, right. I have a container, okay. I have particles in the container and there is a continuous medium, okay. What are the forces acting on the particle? Of course, one we already said, right, gravitational force. Van der Waals forces. Yeah. See, I just want to make a distinction. So, there is now, so let me put it this way. Let's talk about the forces on the individual particles. Okay, let's put it that way. Okay, okay, right. That's what I've written here. Right? This is forces on the individual particles in the dispersion. Okay, definitely gravitation is one. Right. Everybody agrees. Right. Anything else? Buoyancy, I mean, if you say a net gravitational force, that takes care of buoyancy as well, right? Okay. Anything else?
So, this viscous force or no?
Viscous force, okay. Mm-hmm.
The charges and all, forces, static charges and all.
Electrostatic charges. I mean that see when you talk about okay, let's say like this, right. So, I have a particle, okay, I have this, that is charged, okay. Now, the electrostatic interactions become important if I have a very dilute fluid, right. There is absolutely nothing nearby, okay. Then electrostatic interaction, electrostatic forces, I don't see, you talk about electrostatic forces between two things, right.
Yeah.
I mean, even if you look at Coulomb's law, you have charge 1, charge 2, right. This is a force of repulsion or attraction depending upon nature, right. How about hydrodynamic force? You heard of this term, hydrodynamic force? These forces come into picture only whenever there is a flow, right. Now, if you look at particulate systems, right, which if they are tiny enough, the particles are moving, right, okay. The particles are moving. Now, whenever you have a particle moving in a fluid, you have what is called as a drag force, okay, which acts in the direction opposite to the movement of the particle, right. So, the second force is a hydrodynamic force, or you can also call it as hydrodynamic drag force. Third force, there was a Brownian force, okay. And lastly, something called as a osmotic pressure force, osmotic pressure force.